Welcome back, everyone. In this video, we will understand another important machine learning application, which is image classification. Image classification has been very well studied over many years, but it's a very easy to understand beginner project through which I will introduce some of the very important concepts which are widely used in the industry. It's a fundamental task in which we want to teach computer to recognize and categorize objects. Uh, in summary, we will see a simple algorithm, which will be a machine learning model that will automatically classify or assign a label to an input image. This is more like a multi-class classification problem that given an input image, it can be many different classes. But at any single input image will be of always of one class. It has many applications. For example, in object recognition, we want to label or identify objects within images. Medical imaging, such as diagnosing diseases on X-rays, MRIs. Many autonomous vehicles uses some kind of image recognition as well, which it recognizes and reacts to objects in the surroundings, such as stop signs, pedestrians, and so on. Security and surveillance has another important use case where we want to say identify certain kind of objects in security footage of people's even. It is also kind of biometric use case where we want to verify different, say, facial recognition, fingerprint analysis, and so on. In many of these applications, we have to process the data through a certain pipeline, and then labeling of the data has to be taken care of. Further, more and more complexity arises in many of the different use cases. In this one, we will look at a beginner task. Before we go there, let us look at some of the key concepts which are important here. So there is classes and labels. Classes are kind of set of predefined categories, you can say, into which that image can be classified. Each class is a distinct object. For example, an animal or a concept, something like that. The data has to have labeled during training. So training data are assigned some of these classes or category. Next, come to the training data. So this is the data through which the model will learn. So machine learning entirely builds on the data-driven concept where we want to learn this complex relationship from the training data itself. This is kind of its novelty through which it has outperformed many of the domain analysis tools where we don't need complex heuristics or conditional if-else kind of statements or many of the traditional signal processing Fourier transforms. All of these complex things can be learned directly from the data, but we need a very good quality training data. We will look into the sample model training, but this is a phase where model looks at the training data, it just says internal parameters, and it learns so on. This example will directly show us a working training code, but we will later on dive deep into how this training actually happens. Then finally, we want to test and evaluate how the model looks like. We will see some test images here. Many different concepts evolve around. For simplicity in this one, we will directly use the test images to see how the model performs. Overall, in summary, it's a kind of crucial task in computer vision, which allow machines to understand and interpret visual information. Automatically, image classification has many different applications like we saw earlier, but it's also an active area of research and development in artificial intelligence. We'll start here with TensorFlow libraries, and we will load some sample data sets. We will use Matplotlib for visualization. Here, let us look at the CIFAR10 dataset. CIFAR10 dataset is a very popular dataset, which has around 60,000 images, where 32 by 32 is the image size. So each image has 32 by 32 pixels. It's not a very high resolution image, but it's a good enough size for model to learn and classify. There are 10 different classes in CIFAR10. And these classes are, for example, different objects for animals like airplane, automobile, bird, cat, deer. We will classify data set into these 10 different classes. Again, CIFAR10 is used to benchmark many of the machine learning models. So it's a very good beginner project to understand and play with image classification use cases. Each image is 32 by 32 pixels, as we said, but it's a color image. So it has 32 by 32 and 3 pixels to denote the color. Often understanding data is one of the most important part of ML. Now let us load the training data. Here we will load it directly through the dataset which we earlier imported from the TensorFlow itself. And then we will also scale the data later on for processing, because as we know, all the 3 pixels, their values are varied from 1 to 255, so we'll scale them. Let us load the data from the CIFAR10. And now let us visualize what the data look like. So these are the class labels which we will assign. We will randomly select, say, 5 different images for visualization, and we will plot them. And let us look at how these 5 images look like. So like you see, there's a dog image, horses, sheep, truck, different kind of trucks images. And we see this truck image is kind of a little bit confusing. This sheep, we can visually make out that this is sheep and this is a dog and horse. Before training, we'll scale the images. So as discussed, if we don't scale, model will still learn. Scaling actually helps the model to learn it more easily. Here we will define a simple convolution neural network, a CNN. Convolution neural networks are building blocks of vision, and they also are now widely used across many other use cases as well. But CNNs have revolutionized our understanding of the visual processing in neural networks. This is simple neural network. It has many layers which are added here. First, we add a convolution layer, followed by max pool layer, another convolution layer, and another max pool layer. There are like CNN1 and CNN2 layers which I've added. Finally, because the CNN layers kind of are 3D layers of processing the data, we finally want an output which is more simpler, like the 10-layer output, 10 different classes. Before doing that, we flatten the model, open up the layer output, add a few extra dense layers, and finally an output layer. You will see there's some tricks we have to do here, like activations have to be defined. There are different activation functions for these layers. This is a complete example to give a flavor. We will dive deeper into many of these concepts as well as we grow this channel further. Again, there are names assigned to this layer, not compulsory, but they help us to later on visualize them better. Finally, once the model is defined, we also have to kind of compile the model. Compiling the model is kind of a step which tells which optimizer to use. For example, this model has to learn the parameters. Many different optimizer available. We are using an ADAM, which is very widely used optimizer. What is the loss function? How will the model know it's doing good or bad? Loss function is an entropy loss function. And again, we will monitor the metric of accuracy here. In this model, let us look at the number of parameters which we just defined. Through this simple code, we have defined around 12,000 parameters. So you see most of the parameters are actually happening from this dense layer around 9,000, and then convolution layers are very light on the parameters. So these are the layers which internally assume how even human visual cortex, some of the motivations come from that. And that's why putting some restrictions on the layer reduces a lot of parameters. After defining the layer, let us train the model. We are training here the model for 30 epochs using training data, training labels. For validation, we are directly using the test data. Oftentimes in real world, validation can be done in many different ways, and we have defined a batch size of 128. I will share this notebook in the video description, so you all can play it at your end, but you will see some outputs is coming. So for each epoch, the loss which model has is going on decreasing, the model is trying to learn. Accuracy on the training data is increasing, it already reached 50%. And these are 10 different classes. So model at 50, 60% is doing reasonably fine. We want it to go higher. Validation loss, again, the test data, which is part of the validation, you see that validation loss also goes on decreasing, validation accuracy increasing. The larger the data, more times it takes to train the model. Here, there are 60,000 images. So it takes some time for the model to learn up to 30 epochs. You can play with up to 100 epochs as well on your end, but 30 epochs is good enough starting accuracy for this model. As we saw, this model has only 12,000 parameters. You can make this model more complex, add more CNN layers here, flatten them out later on, add more dense layers, a few of them. There are a few other tricks here to play with some specialized architectures. Other tricks like you can avoid model overfitting and so on, which we'll discuss later. But you see, even the simpler model is very, very powerful. It can outbeat a few decades ago years of research easily when the 1990s and early 2000s. So very hard to train such a models, but now it can happen with fingertips. What is the test accuracy for this model? Model already has around 64% test accuracy. It's also easy to look into how the model learning happened, like what is the training accuracy and test accuracy and how did it look like. Let us look at the train accuracy and test accuracy. So the training accuracy in the blue curve goes on increasing, test accuracy, like you see, it's slowly flattening out, but it goes on increasing, and both of them are very close to each other. So model has not overfit, model is doing very well. Let us look at some of the predictions. We can get a prediction from the model using model.predicted and the test images as the input. We'll take around 5 predictions from here, but you can change this in your fun times. Let us look at how the model predictions look like. We are predicting on the test data. So this is a dog and model is predicting this as a bird. A little bit confusing. Maybe dog and bird are looking similar to the model. This is a horse and model is predicting it as a horse. Very good. This is a deer and model is predicting it as a deer, like you can see the deer shape here. This is a frog, model is input actually true, and model is predicting as a cat. It looks like a frog, but the image is a little bit of less resolution, so hard to know. This is a dog, model is predicting it as a dog, so model is doing well. We can actually take few other random samples as well and see what model is doing there. Let us take a few other random samples as well. Bird and model is predicting as a dog. A little bit confusing for the model. Like you see, the dog here is again white color, similar patches. Dog and dog, horse and deer. It was horse, model predicting it as a deer. Automobile and truck. So this is a reasonable confusion where truck and automobiles look similar. It's a bird and model is predicting it as a deer. Like you see, model has learned well. It's a 60% accuracy or so, but we can make it better. And to make it better is actually to make this model more complex, and so that it can learn more better and improve its accuracy further. We will look into some of these changes in the next few videos. Have a good day, everyone. Thanks for joining my video.